fifth lecture, and today we are talking about the cow experiment, unrelated to the animal, just named after its inventors. So we are going back a bit to more mundane topics, away from the question of interpretations in quantum mechanics and philosophical ideas, and the question of the collapse of the wave function. And we come back a bit to what we were asking at the beginning of this lecture as a motivation. We were considering the question, how do we describe gravity in the regime of non-relativistic quantum mechanics? So if we look at a quantum experiment in the lab, how does this behave in gravity? And of course, we can come up with all types of interesting theories as theoretical physicists, and like them or not like them because of aesthetical reasons or because they solve some inconsistencies, or whatever. But in the end, doing physics always means that we compare our results with the real world. So we want to see what happens in an experiment. So from this perspective, the question, what do we actually know about gravity in the regime of quantum physics, comes down to the question, which experimental facts do we have about this regime? Which experiments do we have that test quantum mechanics and gravity in one system together? And there are in fact such experiments, and essentially there are two types of experiments at least, several versions of those, but they are basically just doing the same experiments with different systems. And the most famous one is the so-called cow experiment. It was the first experiment of this kind. It was performed in 1975 by Colella, Oberhauser, and Werner. That's why it's named cow, after their initials. And the one thing that is tested in these experiments is the Schrödinger equation in a Newtonian gravitational potential. So the Schrödinger equation, as you know it, I h bar psi dot equals minus h bar squared divided by 2n times the Laplace operator psi plus e psi. And this for a potential that is the Newtonian potential in a homogeneous gravitational field. So V equals m times g times z. And so this is basically, if you really want to put it like, what do we know as an experimentally established fact about quantum mechanics together with gravity, then this Schrödinger equation is the only thing that we really have, that we can rely on. So today we want to talk about this experiment, what the experiment actually did, and how it confirmed this equation. And for this, we can have a look at the original setup from the original paper first. So here you see the setup that they had. It was an experiment conducted with neutrons. So you have neutrons going through an interferometer. The interferometer was just cut out of a single crystal, a block of the size of about 10 centimeters. Is what you see here on the left. So it was a single crystal that neutrons can go through, and then they essentially go through what acts as like three mirrors, acting through Bragg neutron beam gets split up in two possible paths. So it then enters the second plate at the points B and C, where it again gets reflected. Gets reflected to point D, and where the two beams merge again, and then pass through and can hit several detectors. So we are basically only interested in what happens at one of those detectors. Say we take C2 randomly, and so this is a simple interferometer, and you also know how we can treat something like that in quantum mechanics or also in optical situations. Essentially, we are interested in the path length that the particle takes and how it compares to multiples of the wavelength of the particle. So if we have a difference in the two paths that differs by an odd multiple of half a wavelength, then we get destructive interference, whereas if we have an integer multiple of the wavelength, we will find constructive interference at those detectors. And yes, so this experiment was done then in the gravitational field of the Earth, and the gravitational field is essentially turned on and off by simply rotating the whole interferometer. So if you just rotate the plane of interference, then you're exposing the pattern. You're exposing this path to a gravitational field along this plane ABCD, or you're turning it off by rotating it on. So what happens intuitively is when you have a neutron coming in, and the neutron gets split up into a higher path. Let's say we go from A, we have to go up to reach point C in the gravitational field, whereas the other particle just travels on to go to B. And now the particle that is further up has to uses energy against the gravitational field. So it's at a lower energy level, and therefore, if you remember the Schrödinger equation, then you find a time evolution that is so if you have stationary state, for example, in the Schrödinger equation, where you can separate your wave function into the time dependent part and the spatial part, then you always find that the time dependent part is proportional to an exponential I e t divided by h bar. So if we have an energy eigenstate, for example, then we know that in time it will just oscillate with this energy E. So its phase will just oscillate with this energy E. So if we have the situation as in the cow experiment, so we have the lower path here from A to B, and then the photon goes, then the neutron goes up, and alternatively we have the path where it already gets to a higher gravitational potential here. So then there is essentially a delta E here that is just m times g times z, or delta z. So this energy difference now leads to the neutron that's taking the upper path will need energy against the gravitational field. So it has a smaller energy by this delta E. So its phase along this path, its phase will oscillate a bit slower. And the other one going along this path still has this energy delta E, so its phase will oscillate faster. And and then they will obviously. So here you have a change in the frequency then in this picture, and they will meet here and will have collected a different phase because of this difference in energy. So this is the intuitive picture. Basically, you just need to put energy in, and therefore you get a slower oscillating path phase along the one path than on the other. So you end up with a phase difference here that gives you an interference pattern. To understand this a bit more rigorously, really in the terms of quantum mechanics and of solutions of the Schrödinger equations, you have to make certain approximations. You have to assume, for example, that you find a wave function that is well localized in momentum space. So it has a very narrowly defined momentum. And it is then, of course, because of the uncertainty principle, it is then relatively wide in position space. And then you can approximate it as a plane wave. So the wave that travels here can be approximated as basically a superposition of a plane wave going the one path and a plane wave going the other path with some wave vector along some wave vector, okay, either this one or this one. In this way, you can make sense, also from the perspective of the Schrödinger equation, you can make sense out of this this type of semi-classical approximation where you have the classical path and basically just have this phase difference. In order to understand a bit more in detail how this works, how from the Schrödinger equation one actually gets this result that there is an interference pattern here at all. First, in the absence of gravity, so just why is there interference in this interferometer? That is not based on just this intuitive argument of like path lengths, but really based on the Schrödinger equation. I would like you to have a look at a paper. So there is a review paper by Greenberger, and so it was a longer review article where he discusses all different aspects of this particular neutron interferometer, including the gravitational effect. And I wanted to have a look at one particular section of this, section 2 of this paper. In section 2, he describes how we get an interference pattern in general without the gravitational field. Yeah, so this is the assignment for this week. I put the paper on the Moodle page, so you can download it there, and please just have a brief look through the section to get an understanding, okay, how this ad hoc argument with there being an interference pattern for equal path lengths actually relates to the solutions of the Schrödinger equation. And then from this, if we have established this fact, then we can now start discussing the situation with gravity and the question, how does the gravitational potential change the interference pattern that we see? So this is the next section we're coming to now. So once we have established that the interference pattern just follows the usual way that the Huygens principle, which we also know, for example, for the double slit experiment, that basically the path length determines whether we have constructive or destructive interference. Then the question is, what is the effect now of our gravitational potential? And we assume that the gravitational potential gives a relatively weak effect, so it's a relatively small force compared to the other forces. Hence, we are asking what is the effect if we have a small potential in our Schrödinger equation. So we start with the assumption that we know the solution of the Schrödinger equation without gravity. We call this solution psi0. So we know IH bar psi0 star equals minus equals minus h bar squared divided by 2m Laplacian psi 0. And now we assume we also have a potential that we call u0. So plus u0 psi 0, where the potential u0 contains all the interactions that are going on in our experiment that are not gravity. So in particular for the interferometer that we have in mind, u0 would contain all the reflections at the mirrors, all the Bragg reflections are described by this potential u0. So this is what essentially gives us the splitting in the two paths and the recombination into one path. Now, once we have this, and we know from the previous consideration, that the solution, that psi 0 can be approximated to be a plane wave. So psi 0 is approximately e to the I k0 dot r. So it's just a plane wave propagating along some direction that is given by this wave vector k0. And now we want to solve the Schrödinger equation. We want to solve the Schrödinger equation with the gravitational potential. So we are looking for solutions to this Schrödinger equation, with the assumption that the potential V is much smaller than the kinetic energy of the particle. The kinetic energy for V is much smaller than T, and T is the momentum squared, or if we have the wave vector k0, then that's h bar squared k0 squared divided by m, divided by 2m. So this we assume to hold, and if we have such a small potential, then we do not expect that the potential has a large effect on the shape of the wave function. So our wave function that is very wide anyway, so that it can be approximated by a plane wave, will not be changed much in its shape by such a big potential. So we can make the ansatz that there is only an effect on the face of the wave function. So we make the ansatz that psi of r is just e to the I phi of r represents phi times our psi 0. And now we insert this ansatz into the Schrödinger equation here. So with this ansatz, and I copied this from my notes, so I don't make a mistake. So with this ansatz, we find IH bar e to the I phi psi 0 dot equals, and now from the kinetic energy term, there will be three terms. There's first the one where both derivatives act on psi 0, so this gives us minus h bar squared divided by 2m e to the I phi Laplace of psi 0. Then we have we get two terms that are mixed, where one derivative is acting on e to the I phi and the other on psi 0. So this gives us minus IH bar squared divided by m e to the I phi nabla phi dot nabla psi 0. And then we get the term where both derivatives are acting on the phase. So plus h bar squared divided by 2m e to the I phi Laplace phi psi 0. And finally, the two potential terms, which are just multiplicative. So plus u0 e to the I phi psi 0 plus v e to the I phi psi 0. So if we have this, we can just insert the free solution here for our psi 0 dot. So for this, we just find that this is minus h bar squared divided by 2m e to the I phi Laplace psi 0 plus e to the I phi u0 psi 0. So this term will cancel with this one, and we will find that this potential term will cancel with this one. So I made some space here, and again, I just refer you to the lecture notes on the Moodle page if you want to keep track of the equations that we have already. So now what we get from this is we have 0 on the left-hand side, and we are left with minus I h bar squared divided by m e to the I phi nabla phi dot nabla psi 0 plus this term h bar squared divided by 2m e to the I phi Laplace phi psi 0 plus the potential term here. I don't need this anymore. So we can first now we can multiply everything with 2 times the mass. And we can get rid of the e to the I phi everywhere. And now we insert our plane wave solution. So we insert psi 0 equals e to the I k0 dot r, and also divide by psi 0. And then here we get the gradient I k0. Plus here, and the I vanishes, and we get gradient k0 here. So we are left with this equation, and now let us have a look. So now what we require is that the phase only changes a little bit over the distance of one wavelength. So we require that the derivative gradient of phi much smaller than 2 pi divided by lambda. So the change over one wavelength lambda should be much smaller than 2 pi, which is k0. Okay. And this implies that that terms that absolute value of the Laplacian of phi terms, which is somehow of the order of nabla phi, if you want, that this should be much smaller than nabla phi dot k0 terms. So, meaning that in the equation, the second derivative term of phi, Laplacian of phi term, we can neglect in comparison to this first derivative term. So this term is much smaller, and therefore we neglect it. And what we are then left with is the following: is Laplace phi dot Laplace k0 equals minus, and then we have mb here, m divided by h bar squared, the potential v. And now, in order to solve this equation for the phase, first see that the momentum of our plane wave is h bar k0, and we can write the momentum also as mass times the velocity, or as m dr0 by dt, where dr0 basically parameterizes the path of our particle, and if we insert this into our equation, then what we get is that we have gradient phi of our dot dr0 equals minus 1 over h bar v dt. And this we can integrate. So if we integrate this, we find that the potential phi at the particle position r0 of t is given by, well, the initial phase minus 1 divided by h bar, the integral of our potential, integral from 0 to t dt prime of our potential at the particle position r0 of t prime. So this equation determines now the phase shift of our wave if it goes through this potential v. So now that we've understood how a small potential affects the phase of the wave function in general, let us go back to the scenario of the cow experiment and look at the particular example of the phase from the gravitational potential. So first, we should choose a smart setup. So if we have our gravitational potential pointing downwards, this is our gravitational acceleration. Then the setup in the cow experiment is such that the incoming beam is orthogonal to this. And then at point A we have our first Bragg reflection that reflects down here. Where we have the second Bragg reflection, this is point C. Back here is point B, where we have another Bragg reflection, and we have point D here. So this is the setup, and we use some colors. So we can draw the symmetry axis of the experiment here. Be this one. And the angle here is called theta. This is the angle between the incident beam and the symmetry axis of the experiment. So the experiment, our mirrors or plates would actually be orthogonal to the symmetry axis. And now we can so we have at equal time, I didn't represent this properly here, but at equal time the beam will arrive at the points B and C, and if we have 2 points here that we call P1 and P2 that are also the same distance away, then now we can look at the difference in potential at those 2 points. So we are interested in the potential difference, potential at P2 minus the potential at P1. And you see, this is essentially so this is the height difference. So we need this length, and we have this length, which is x. Then you find that so this is called B, and you find that D is just 2 times x times the sine of beta. So this would be the first part. And now the second thing is that, well, instead of having the full gravitational acceleration here, we actually have an acceleration g alpha, which we get from rotating the whole interferometer around this axis. So if we rotate it, that it is parallel to the ground, then we won't have any potential difference. So we will have no gravitational effect. And if we put it completely upright, then there will be the full gravitational potential acting. So our G alpha is also proportional to the sine of this rotation angle, which we call alpha. So it's G times sine alpha, depending on how we choose the angle alpha. Now, what we need to also take into account. So first, so this potential, I wasn't finished here. So this potential is m times G alpha times d. Or if we use what we know here, then this would be 2m times G alpha times sine theta. G alpha sine theta. Now, if you look at this and you ask what is the velocity? What is the velocity of the particle through this experiment? Then you see, so if we are at time t, we are here at our points P1 or P2. So the distance traveled is like this one. The distance traveled will be x divided by cosine theta. So this is x divided by cosine theta. So we have v times t is the distance traveled equals x divided by cosine theta, or we can write this as, if we take the derivative of x, we can write this as dx by dt is v times cosine theta. So this is the velocity along the central axis. So with this, we can now write down our phase shift. And we just look at the phase difference between the two waves. We look at the phase difference, delta phi, between the between the upper path and in the path that goes down. So this is what we've seen in the previous section. This is minus 1 divided by h bar. Remember the offset, the zero phase just cancels of the two parts. So it's minus 1 divided by h bar, integral from 0 to t. And now it's the delta v of our potential at t prime dt prime. Now we just insert our delta v here. So we can write this as minus 2m g alpha divided by h bar, so all the constants, integral 0 to t, and what we have left is x sine theta. And now we substitute. We use this to substitute t by x. We parameterize with x. So we find minus 2m g alpha divided by h bar 0 to x of t. And now this would be x prime sine theta, and now instead of dt prime, we find dx prime divided by v cosine theta. And now you see that this is just, so those are constants, so this gives us a tangent of theta. We have the v here. So all in all, we find, and then the integral over x prime just gives us an x squared half. So this cancels with the 2, so we find minus m g alpha divided by h bar. Then we have the v here. We have tangent theta x squared. And now let me make a little bit of space. Space up here. So now if we're interested, so this is our delta phi of t if you want, so this is just the delta phi at 2 points p1 and p2. And now if we're interested at our delta phi between the points b and c, phi, let's call it delta phi bc. So the delta phi we have at the points b and c, then you just put in this length. So from here to here all the way. This length is L. So we have L instead of X. So we find that this delta phi equals, I do two things at once. So we want, so the phase shift to this points B and C is a delta phi where we have L squared here. And then for symmetry reasons, you will have exactly the same phase shift again until we reach point B. So we actually calculate our final phase shift here at B. So we get a factor of 2. And then we have minus, and then we have m g alpha divided by h bar v tangent theta L squared. And now we can use that the area, the total area of our interferometer here. So this area is 2L times tangent theta, if you calculate it. So 2L squared times tangent theta. And so if we insert this, then we find that we can express the phase difference delta phi as minus m g alpha times the area of our interferometer divided by h bar v. So we see that there is a phase shift, there is a phase difference. The phase difference depends on the mass of the particle we have, in our case a neutron. Obviously it depends on the strength of the gravitational field here, G alpha, which is the one that will then depend on the rotation angle and give us the sign pattern. It's the larger, the more area we cover with our interferometer, and it's the larger, the smaller the velocity of the particles. So we need particles that travel slowly through our interferometer and cover a large area. So we can plug in some numbers, and again, I make a little bit of space down here. So we have established now that that there is some principles that show phase shift. Now the question is, can we actually observe the phase shift? And if you think of the experiment by Colella, Oberhauser, and Werner, then what you find is that the total length of this interferometer, so 2L in their case, is about 10 centimeters. So that gives, with the opening angle they have, that gives an estimated area that is 10 centimeters squared. We insert the neutron mass, which is roughly 1.7 times 10 to the minus 27 kilograms. You see that's a relatively small value, so it's a legitimate question if we will see anything. And then the question is, what velocities do we have? Well, if you have neutrons, those have typically velocities, like thermal neutrons that were used in this experiment, have typical velocities of about 1,000 meters per second. And those are all the parameters. And now we want a phase shift that is measurable. So we want a phase shift that's like of the order of 1 somehow to measure something. And now if we insert all of this, if you insert those numbers, you will find that so this means that we require a G alpha that is H bar V divided by NA, roughly. And with those numbers inserted, this gives you an approximate 0.06 meter per second squared. Okay. So you see that the gravitational acceleration in the Earth's gravitational potential, which is roughly 10, is more than sufficient, actually by like almost 2 orders of magnitude, sufficient to give this phase shift. And well, the reason why that is because although this mass here is tiny, you also have this tiny factor of h bar in the denominator here. So this h bar in the denominator gives you a huge increase of the effect and makes it possible to observe this phase shift in this scenario. So I mentioned at the beginning that there are 2 experiments that have been done where both gravity and quantum mechanics play a role. And the second experiment you see depicted here. So this is an experiment that is much more recent. That was done by Novichevsky and others in 2002, so about 20 years ago, compared to the Cow experiment that was done like 45 years ago. What they did is they also used neutrons, but they sent the neutrons, they shot these neutrons in between or onto a mirror or a surface that is perfectly reflecting for neutrons. And so the mirror is the only really important part here. You have the mirror and you have the gravitational potential. and because of that, you get the neutrons in the z direction become trapped in this potential that is built by the mirror at the bottom and the gravitational potential. And then in this z direction, you actually find stationary states, energy eigenstates, and those are shown on the right hand side. So in formulas, the potential here is the potential that is Newtonian gravity, so mdz, but only for positive values of that, and it's infinite for values of z that are smaller than 0. So if you plot this, then we have a potential like this. And and in this potential, you can then find stationary states. We will briefly discuss this and come back to this in the next lecture when we talk about the equivalence principle. But this is more for a sake of completeness. So there are in fact two different types of experiments that have been done with quantum systems in the gravitational field. There have been other variations of those. For example, the Cow experiment has been done with atoms also, in addition to neutrons. But essentially, the state of the art of experiments that test both gravity and quantum mechanics together is the only thing that we know are point particles that solve the Schrödinger equation in a Newtonian gravitational potential. So we know that to this effect, as far as gravity and quantum theory can be approximated by this particular Schrödinger equation, this is correct and experimentally confirmed. Everything else is basically still open to speculation and hopefully to finding experimental facts that we can, or finding observable facts that we can then test in experiments. Okay, so with this, I'm at the end of the lecture today. And yes, next week we will talk about the equivalence principle.